Lesson 18 is about circumference and arc length, and in 18.1 we're just going to review what the circumference formula is for a circle but not do any examples with it. So the circumference of a circle with diameter d and radius r is, there's two formulas. You can do circumference equals pi times diameter, pi times d, or circumference equals 2 pi r. You'll see them written both ways. The diameter is just double the radius. So the reason that there's kind of two different formulas is you have the 2 times the radius over here times pi versus just the diameter times pi here. Either one works, so it's kind of nice to know both though. Okay, so 18.2 is called arc length. So arc measures the, or equals the measure of the central angle that intercepts the arc. So like if we look at these two pictures, there's arc AB right here, and the central angle that intercepts it is 54 degrees. So the measure of that arc would be 54 degrees. So that's arc measure. It's given in units related to angles, like degrees. So that's why we say it's 54 degrees, not just like 54 or like 54 units or something like that. This measurement doesn't depend on the size of the circle. So you can see like on circle C on the left, that's bigger than circle F on the right. But arc DE is also going to be 54 degrees because it's intercepted by the same size central angle as arc AB. So they both have a central angle of 54 degrees that kind of connects to each of their own arcs. Definitely the arc in circle C would be longer, but the arc measure is the same because the arc measure doesn't depend on the size of the circle. Kind of like how in a circle there's only 360 degrees no matter how big or how small the circle is. So that means that changing the size of the circle isn't going to change the arc length because you still ultimately at the end of the day just only have 360 degrees to work with. Okay, arc length is a fraction of the circle's circumference, so it can be given by a formula where a fraction is multiplied by the circle's circumference. So before we get into kind of like creating the formula, think of like if we have, you don't necessarily have to draw this, but if I have a circle and let's say my arc is like a semicircle. So it goes like halfway around the circle like this, it connects to the diameter. And so if I wanted to find the length of that arc, and it's not the arc measure, but the length of it itself, since it's half of the circumference, I could do 1/2 times the circumference because it's half of the distance all the way around the circle. So just to give a little visual. And then now if we want to start to kind of like put the formula together, it's going to be the arc length is equal to the fraction, which that means like what fraction of the whole circle is it? So we just talked about like how the semicircle is half. Basically like what portion of the circle does the arc take up? So is it like a third of the circle? Is it a quarter of the circle? And so on. And then times the circumference. And then now we can start like kind of piecing together like actual values rather than just like kind of names them like fraction, circumference, stuff like that. So we know the circumference formula, so we can put that in there. So it'll be arc length equals the fraction times 2 pi r. That's our circumference formula. So arc length is going to be the fraction of our arc times circumference, which is 2 pi r. Or pi times diameter. The reason you see 2 pi r a lot, even though that feels like less simplified than pi times the diameter, is because you're given the radius more frequently than you're given the diameter. And then now we can kind of like, I guess, create a little like formula for how to find the fraction. So we'll have arc length equals, when you're trying to find the fraction, if it's not as clear, it's just like it's half or it's a third or it's a quarter. You can find the fraction by taking the arc measure and putting it out of 360 because it's like your part, that's the arc measure, out of the whole 360. So that's what fractions are, parts out of a whole. And then that is going to be multiplied by the circumference. So altogether, our formula is going to be arc length equals the arc measure, that's the one in degrees, over 360 times the circumference 2 pi r. Okay, example 1, find the length of arc AB using arc length equals arc measure over 360. That should be a multiplication symbol, not an equals, but times 2 pi r. I'll make sure that's fixed if in case anybody prints them. But now we can just kind of put in all the information that we know, and it'll spit out our arc length there. So we'll start with arc measure. So arc measure is going to be the same as like the central angle. So for arc measure, it's this like measurement right here, which we don't have labeled, but like I said, it's going to be the same as the central angle, and our central angle is 45 degrees. So our arc measure is also 45 degrees. So we'll put 45 degrees in there over 360 degrees. And then times the circumference, so 2 pi r, and then we know the radius here, it's 3.5. So we'll put 3.5 in for r. Okay, so one more time, we just went ahead and put our like arc measurement in there, and then we put our radius in for r, and that's really the only two like things that you need to put into this formula. So before we get into simplifying, I just want us to kind of like conceptualize what this formula is saying. So to find the arc length, we're finding a portion of the entire circumference. So if I were to find like the entire circumference, that would be 2 pi r. But I don't want the entire circumference, I want just a portion of it or just a fraction of it. And so to find the size of the fraction that I need out of that entire circumference, I'm taking the measure of my arc out of the whole. So 45 degrees out of the whole 360, and then I'm multiplying that by my circumference, and that's going to give us just the length of our arc. Okay, so now we can go ahead and simplify. Most of the time, probably all the time, you're going to have to end up reducing your arc measure over 360 fraction. So in order to reduce, you don't want to just straight up like divide it like 45 divided by 360, because a lot of the like multiple choice answers will leave you with fractions. So you want to truly reduce it. You need to think of a common factor. So first one that pops in my head is 9. So I'm going to divide numerator and denominator by 9. And you don't have to like get the greatest common factor like right away. You can just like divide both by 3 and then work your way down from there. You can kind of approach in different parts. So 45 degrees divided by 9, it's going to leave us with 5. I'm also going to take the degree symbols off because they would cancel each other out. So 45 divided by 9 is 5, and then 360 divided by 9 is 40. And then times, over here I can multiply the 2 and the 3.5. I'm going to leave the pi alone for right now. So 2 times 3.5 is 7 pi. And then I still have a common factor here. I can still reduce like the 5 and the 40 more because those are both divisible by 5. So I can divide both by 5. So 5 divided by 5 becomes 1, and then 40 divided by 5 becomes 8, and then times the 7 pi over here. And now we can just multiply straight across. If you want to, you can think of like 7 pi as 7 pi over 1. And then we'll multiply like numerator and numerator, so it'd just be 1 times 7 pi is 7 pi. And then over 8 times 1, so over 8. So the length of our arc is going to end up being 7 pi over 8. I've noticed some of the problems in Canvas, some are like written like this with pi in, and some have it like multiplied in. So if you need to get like a decimal approximation, the way that you would do it is you can use, if you have a calculator that has like the pi button, you can use it, or you can use 3.14. So you do 7 times 3.14, and then you would divide that by 8. So just multiplying the numerator, so do 7 times 3.14, and that's 21.98, and then you can divide that by 8 in the denominator, and so you end up getting approximately 2.75. So it's helpful to kind of be able to get to both answers depending on like what type of responses are available to you. Okay, so finding the arc length, you're taking your fraction, which is your like arc measure out of 360, and multiplying it by the circumference. Example 2, in circle D, endpoints E and F are endpoints of the diameter. So like green line in the circle or green segment is the diameter, and the length of EF is 9 pi units. What's the radius of circle D? So in this case, we're given the arc length, and we're given well, we're not really given the central angle, but we can definitely find it, and we're asked for the radius. So we can still use this formula up here, even though this formula is kind of created to find arc length. We can kind of use it, I guess, as a way of solving for the radius because we know arc length. So it just changes around like what our unknown is. So I'm going to copy this formula down. I'm just going to say like AL for arc length. No, I'm not. I feel like that looks weird. Okay, I'm just going to write it all out. Arc length equals the arc measure I'm going to shorten measure just to that. So arc measure out of 360 and then times 2 pi r. Okay, so we can just kind of start filling in things that we know. It says that the length of EF, which is that arc, is 9 pi. So we could put 9 pi in right there for arc length. And then equals the arc measure over 360. So I'm just going to copy down the 360. The arc measure, it's not labeled on the circle, but remember it's going to be the same as the central angle that connects to the arc. So that's this angle right here, and that's not labeled either. But since that's a diameter, it means that this is like a semicircle. So that means that the central angle and the arc measure would both be 180 degrees. So always when if this segment is a diameter, it's cutting it exactly in half, and half of 360 is 180 degrees. So the arc measure is 180 degrees. So we'll put 180 in for the arc measure, and then times 2 pi r, which 2 and pi are just numbers, but r is what we don't know, so that's just going to stay as is. Okay, so before we move on to kind of simplifying, I just want to show like a little bit different way of setting this up in case you like just kind of have a brain fart and you can't figure out what the arc measure is. Remember that this part right here is just like the like kind of fraction of your arc out of the whole. And so if you know that this is a diameter, if EF is a diameter, then it cuts the circle in half. And so your fraction would be 1/2. It's half of the circle. And then similarly, like if we just take 180 over 360 and we reduce it, it's going to reduce to 1/2. So you can approach it however you want. If you don't need the full formula as far as like arc measure out of 360 to figure out what portion of the circle is your arc, you don't have to use it. If you know it's half, just put half. Okay, so back to reducing. Both 180 and 360 you can divide by 180. So we'll bring down our 9 pi equals 180 divided by 180, that's going to become 1, and then 360 divided by 180, that's going to become 2, so it reduces down to 1/2. Of course, it's half the circle because that's the diameter, and then times 2 pi r over here. Okay, and then what I would recommend prioritizing is just getting the right side of the equal sign simplified as much as possible. So if you want, you can multiply straight across and then reduce, or you can kind of like cross cancel if you prefer. So like the 2 and the 2, one is in the numerator, one is in the denominator. So like they cancel each other out and they'd be left with 1. So really all I'm left with in the numerator is pi times r, because everything else is canceled out to a 1. And then I have this 9r over here, so I'm going to bring those down. So it's going to be 9r equals pi times r. And sometimes when we get to this point, it's like, you're like, okay, what is happening? Because sometimes pi looks like a variable, it's really not. So just bring yourself back to like, what is the question asking? So it says, what is the radius? And so that means our priority is getting r by itself. So that means that you have to cancel out the things that are being done to r. So now there's a pi that's being multiplied by r. So to cancel out multiplying by pi, I would divide both sides by pi. So I've seen it a lot where like people want to divide by r, they get kind of mixed up. So if we're solving for the radius, we want this r to just stay right here and we cancel out the things around it. So we're trying to cancel out that pi that's being multiplied by it. Pi divided by pi over here also cancels out, so we're just left with 9. So r equals 9. So the radius of This circle is 9 units. Moving on to 18.3, it's the ratios of arc length to the radius. So we're going to find the ratio between the arc length and the radius of each of these two circles and kind of compare those final values. So down here, find the ratio of the arc length to the radius of each circle. We have kind of like the little formula for our initial setup down below. So for circle C, we're going to take the arc length, which is that 9 pi over 10 right here. So 9 pi over 10. And we're going to put it over the radius of circle C, which is 2.7, and then we're going to simplify. Okay, so for something like this, when you have like a fraction and within a fraction, I usually recommend like writing it out as like more of a division problem horizontally, because that's what fractions are, is they're just like dividing. So we'll do 9 pi over 10, and then divided by 2.7. And then I'm going to change this to multiply by the reciprocal instead of dividing the fraction. So it'll be 9 pi over 10, and then we'll change the division symbol to multiplication. And then we'll take the reciprocal of 2.7, which we can think of that as 2.7 over 1. So we'd flip it upside down, it'd be 1 over 2.7. And then from there, we can just multiply straight across and reduce. You can cross cancel, but it's a little bit funky with the decimal. So we'll multiply straight across. 9 pi times 1 is 9 pi. And then 10 times 2.7 is 27. And then from there we can reduce. So 9 and 27 both have a common factor of 9. So I can divide both by 9 to reduce the fraction without actually changing the value. So 9 divided by 9 is 1. So that just leaves us with 1 pi or just pi. And then 27 divided by 9 is 3. So we end up with pi over 3. So the ratio of the arc length to the radius of circle C ended up being pi over 3. We're going to repeat that same process, but with circle D. So the arc length of circle D is pi over 2. So pi over 2. And then over the radius of circle D, which is 1.5. So over 1.5, we'll approach it the same exact way as the other one. We'll kind of write it out horizontally. So we'll do pi over 2 divided by 1.5, and then I'm going to change it to multiply by the reciprocal. So it'll be pi over 2, and then we'll change the division symbol to multiplication. We can think of 1.5 as 1.5 over 1 and flip it upside down to its reciprocal, 1 over 1.5. And then we can multiply straight across. So pi times 1 is just pi. And then 2 times 1.5 is 3. This time we don't have anything to reduce. We just ended up with pi over 3. So we took the ratio between the arc length and the radius of each circle, and we ended up getting the same exact number in the end, pi over 3, even though there are two different size circles. So two different size circles, they had two different size arc lengths and two different size radius or radii. The only thing that was the same is that the central angle was the same. So that's kind of the key point of this little section, is that if central angles are congruent, then the ratio of their arc length to the radius in each circle is always equal. So regardless of the different sizes, if they're both 60 degrees for the central angle, then the ratio between the arc length and the radius will be the same. So what we just found, the ratio of the length of an arc to the radius of the circle, is called a radian measure. So radian measure is just a different way of measuring angles, a different unit of measurement. So we have both of these circles are 60 degrees. They have 60 degree central angles. If we were to list their central angles measurement in radians, they would both be pi over 3. So in the circle above, the measure of angle ACB, that's the central angle of the circle on the left, is pi over 3. And the measure of angle EDF, that's the central angle on the right, is pi over 3 as well. So radians can kind of feel a little bit overwhelming at first, but I like to think of it and kind of compare it back to, if you're measuring distance, there's so many different units that you can use to measure distance. There's feet, inches, centimeters, yards, miles. There's so many. And for angles, we have degrees and we have radians. So the relationship between degree and radians is they measure the same thing, just in different units, just like feet and inches. Okay, so in general, to find the central angle in radians, you just need to take the arc length and divide it by the radius. That's what we just did. So to find the measurement in radians, you take the arc length and divide it by the radius. Okay, moving down to example 1, it says examine circle D. Circle C is a different circle with radius of 8, arc AB, and angle ACB is congruent to angle EDF. What is the length of arc AB? Okay, so you'll see a few different problems like this, like in checkpoints and in the exam. I would really recommend drawing circle C just to get a visual for it. So I'm going to go ahead and draw it and just label as much as I can on there. So on circle D, the radius is 3, and on circle C, the radius is 8. So it doesn't have to be to scale, but I am going to draw like a little bit bigger circle. And then we have a radius of 8, so I can go ahead and I can label that. So I'll put my center in there and then draw my radius, go ahead and give it an 8, and then label my center as well. Okay, so circle C will also have arc AB, so I'm going to make one of these points point A. And then before I draw the arc, it's important to know that the measure of angle ACB, which is going to be my central angle in my new circle, is congruent to angle ECD, which is the central angle of my original circle. So the central angles are going to be the same. They're going to like open up to the same distance. So I'm going to try to draw like a similar like size slice in my bigger circle as I have in my smaller one. So I'll draw maybe going this way, and I'm going to draw my little kind of angle marker to show that angle EDF is congruent to angle ACB. And it doesn't have to be perfect. I would just try to make it as close as you can. So we have our radius. We have that the two central angles are congruent. And then just by putting that last point there, now we have arc AB. So arc AB is this distance kind of around the outside of the circle. The radius right here is 8, and then our central angle is located, or is labeled with the congruent measure. Okay, so this question is asking us for what is the length of arc AB, which that's the only thing that we don't have labeled because that's the thing that we need to go ahead and find. Okay, so in order to kind of like know how to set up our equation, I'm going to go back up to this section. So where it says if central angles are congruent, then the ratio of the arc length to the radius in each circle is always equal. So we have that the central angles are congruent. That information was given to us. So then that means that we can find the arc length. I'm just going to label it as AL over radius of, let's say, circle D. This is just kind of like not any like formal math writing. I just kind of want to start to spit out something that we can use to set up our equation. So it says the ratio of the arc length to the radius in each circle is always equal. So we have the ratio of the arc length of circle D, and that's going to be equal to the ratio of the arc length to the radius of circle C, as long as the central angles are the same or congruent, which they are. So now we can just go ahead and start kind of like filling in as much information as we can. You can go ahead and start putting in like arc length for circle D, the radius for circle D, and the radius for circle C if you want. I'm just going to go ahead and like kind of create a more like formal setup so it's a little bit easy to refer back to just in case this isn't making a ton of sense. So it'll take me a little bit longer to write it, but you're welcome to work ahead. So we're going to take the length of the arc from circle D, which is EF, that red one. So the length of arc EF over the radius of that same circle, so the radius of circle D, and that's going to be equal to the arc from circle C, which we don't know that, we're going to find it, but that's going to be AB, is this arc right here. So we'll say it's equal to the length of arc AB over the radius from that circle that has AB, which is circle C. So we say over the radius of circle C. And then now we can kind of start substituting in values. So length EF, That's 6.28, so I can put 6.28 in for the length of arc EF. And then over the radius of circle D, which is 3, so I can put 3 in for the radius of circle D. And then equals the length of arc AB. You can leave that as like writing out the length of arc AB, but it's like kind of long to write it. So I think I'm going to assign it a variable. I'm going to call it X. And so where it says length of arc AB, I'm just going to put an X there just so I don't have to write out length of arc AB every single time. And then the radius of circle C, we know that one, it's 8. So we can put 8 in there for radius of circle C. And then now we have something that's called a proportion when you have one fraction equal to another fraction. So when you have a proportion, the most like common way of solving it is by cross multiplying it, which means that you multiply diagonally through the equal sign. So you would do like x times 3, so that's 3x. And then you set that equal to the product of the other diagonal. So 6.28 times 8. So 6.28 times 8 is 50.24. And then one more time, just because I know we haven't done that in a while, you go diagonally through the equal sign, so 3 times x. And then 6.28 times 8 is 50.24. And then our ultimate goal is to solve for x, or for the length of arc AB is what we kind of put x in there for. So if we want to get x by itself, I have to cancel out that 3. So that 3 is being multiplied, so to cancel it out, I would divide both sides by 3. So 50.24 divided by 3 is going to leave us with about 16.75. So these 3's will cancel out, and we'll be left with x is approximately 16.75 if we round to 2 decimal places. So I'm just going to kind of bring back in like the measure of length or of arc AB now to write my final answer. So I'll say, or not the measure, but the length. So the length of arc AB is approximately 16.75. Okay, so when you're given 2 different kinds of circles and you need to find some sort of missing measurement, whether it be the radius or the arc length, you can set up a proportion between the 2 ratios of arc length to radius of each circle. I would definitely save kind of like this setup so that you can reference it in the future.